What if everything we think we know about the universe's beginnings is wrong? Picture this: our cosmic story, the grand narrative of how everything came to be, might not be the tidy, textbook explanation we've been taught. Instead, it could be a wild tapestry of competing ideas, some so radical they defy logic, others so elegant they take your breath away. And that's exactly what we're diving into today. 25 controversial theories about the universe's origin that will make you question reality itself. From the moment humans first looked up at the stars, we've been obsessed with one burning question: where did all of this come from? Every culture, every civilization has crafted its own creation myth, but modern science has offered something even more astonishing: a universe born from nothing, exploding into existence in a fiery Big Bang. Except what if that's not the whole story? What if the truth is stranger, more mysterious, or even unsettling? Some theories suggest our universe is just one bubble in an infinite cosmic foam, while others propose we're living inside a simulation, or that time itself might not flow the way we think. And that's just the beginning. This isn't just about wild speculation, it's about the frontiers of human curiosity, where science, philosophy, and imagination collide. We'll explore ideas from respected physicists who dare to challenge the status quo, alongside concepts so outlandish they blur the line between genius and madness. Some of these theories might unsettle you, others might ignite a spark of wonder you haven't felt since you were a kid staring at the night sky, wondering what's out there. So buckle up, because by the end of this journey, you'll never look at the cosmos the same way again. The Big Bang Theory is the cornerstone of modern cosmology, the story we tell about how everything began, but even this well-established idea isn't as simple as it seems. Imagine the universe not as an endless expanse, but as a single, unimaginably dense point, smaller than an atom, containing all the energy that would eventually become galaxies, stars, and even us. Then, in a fraction of a second, it expanded faster than light itself, setting the stage for everything that exists. That's the Big Bang in its simplest form, backed by some of the most compelling evidence in science. Take the cosmic microwave background, a faint glow of radiation that fills the sky like the afterimage of that explosive birth. It's the universe's baby picture, captured when it was just 380,000 years old, and its near-perfect uniformity tells us the early cosmos was incredibly smooth before gravity sculpted it into the structure we see today. Then there's the redshift of distant galaxies, all racing away from each other as if the fabric of space itself is stretching, exactly what you'd expect if the universe had been expanding for billions of years. Yet for all its successes, the Big Bang Theory isn't without its mysteries. It doesn't explain what triggered the expansion in the first place, what existed before that moment, if before even makes sense when time itself may have begun there. Some physicists argue the theory is incomplete, pointing to gaps like dark matter and dark energy, which together make up 95% of the universe but remain utterly unexplained. And then there are the rival ideas, theories like the Big Bounce, which suggests our universe is just the latest in an endless cycle of expansion and collapse, or the idea of a multiverse, where our Big Bang was just one of countless others bubbling up in an infinite cosmic froth. Even the term Big Bang was originally meant as a joke, a dismissive label coined by a scientist who hated the idea. Yet here we are, still grappling with its implications, still trying to peel back the layers of that first unimaginable moment. Because the deeper we look, the more questions we uncover, and that's what makes cosmology so thrilling. The Big Bang isn't just an answer, it's an invitation to keep exploring. Despite the overwhelming evidence supporting the Big Bang Theory, some glaring inconsistencies have left scientists scratching their heads. Take the horizon problem, one of cosmology's most puzzling mysteries. If you peer into opposite ends of the observable universe, the temperature of the cosmic microwave background is nearly identical, down to a tiny fraction of a degree. But here's the catch. Those regions are so far apart that light from one could never have reached the other, even in the universe's 13.8 billion year lifetime. So how did they reach equilibrium? It's like 2 cups of coffee placed miles apart cooling to the exact same temperature without ever touching. One proposed fix is cosmic inflation, a mind-bending idea that the universe underwent a period of exponential expansion in its first sliver of a second, stretching space itself faster than light could travel. This would explain why distant regions appear so uniform. They were once cozy neighbors before inflation flung them apart. Yet inflation comes with its own baggage. What triggered it and why did it stop? Some critics argue it's less a solution and more a placeholder for deeper physics we don't yet understand. Then there's dark energy, the enigmatic force pushing galaxies apart at an accelerating rate. The Big Bang framework accommodates it mathematically, but no one knows what it actually is. Is it a property of space itself, or something more exotic, like a dynamic field that changes over time? Alternative theories, like modified gravity, suggest Einstein's equations might need reworking altogether, that gravity behaves differently on cosmic scales than we've assumed. But these ideas struggle to explain all the observations as cleanly as dark energy does, leaving us in a tug of war between revolution and refinement. Even the Big Bang's triumph, the abundance of light elements like hydrogen and helium, faces scrutiny. While the predictions match observations almost perfectly, tiny discrepancies linger. Could they be flukes or hints of new physics? Some theorists propose wild alternatives, like a mirror universe of unseen particles influencing ours during those first fiery minutes. Others suggest the cosmos might not have begun with a bang at all, but as a slow unfurling from a previous state of collapse, a big bounce, or even a collision between higher dimensional brains in string theory's tangled landscape. What makes these debates so exhilarating is that they're not just academic, they force us to confront the very nature of reality. Are we missing a fundamental piece of the cosmic puzzle, or are we clinging to an incomplete framework because it's the best we've got? The Big Bang remains our most powerful origin story, but its cracks invite us to dream bigger, to question deeper, and to stay hungry for answers. Because in the end, the universe's greatest mystery might not be how it began, but how much we still have left to discover. Imagine a universe without a beginning, no explosive birth, no moment of creation, just an endless, unchanging expanse where matter continuously forms to fill the void as space expands. This was the bold vision of the steady-state theory, the Big Bang's greatest rival in 20th century cosmology. While the Big Bang told a dramatic story of cosmic origins, the steady state offered something more serene, a universe that simply was eternal and self-renewing with no need for a starting point. The theory emerged in the late 1940s, championed by brilliant minds like Fred Hoyle, Herman Bondi, and Thomas Gould. Their idea was radical yet elegant. As galaxies drifted apart due to cosmic expansion, new matter would spontaneously appear in the empty spaces between them, just enough to keep the overall density of the universe constant over time. Hoyle famously mocked the Big Bang with his derisive label, but his own theory was no laughing matter. It was a serious attempt to explain the cosmos without invoking a singular, unexplainable moment of creation. For years, the steady-state theory held its ground, appealing to those uneasy with the philosophical implications of a universe that sprang from nothing. It fit the observed expansion of the universe and even accounted for the rough uniformity of matter. No inflation required, but cracks began to show as technology advanced. The discovery of quasars, incredibly bright and distant objects, suggested the universe looked different in the past, contradicting the steady-state's premise of an unchanging cosmos. Then came the cosmic microwave background, that faint afterglow of the Big Bang, which the steady state struggled to explain without resorting to ad hoc fixes. By the late 1960s, the evidence had piled up decisively in favor of the Big Bang, and most scientists abandoned the steady state. Yet, like many great ideas, it never truly died. Some modern cosmologists have revisited its core principles, tweaking them to fit new data. For instance, the idea of continuous matter creation finds echoes in theories of quantum vacuum fluctuations, where particles pop in and out of existence. Others speculate that a steady-state-like process might operate in a broader multiverse context, with our observable universe just one slice of an eternal, self-adjusting cosmos. What makes the steady-state theory so fascinating isn't just its scientific audacity, it's the philosophical questions it raises. Can the universe truly be infinite with no beginning or end? Or does our intuition demand a story with a clear starting point? The decline of the steady state didn't spell the end of these debates, it simply shifted them to new frontiers. Even in defeat, the theory reminds us that science isn't just about finding answers, it's about daring to ask the boldest questions, no matter how uncomfortable they might be. While most cosmologists see gravity as the invisible architect shaping the cosmos, there's a provocative alternative that flips the script entirely: the plasma universe, also known as the electric universe theory. Picture a cosmos where swirling currents of electrified gas, not gravity, sculpt galaxies and ignite stars where the Big Bang never happened, and the universe hums with a primal electric energy. This is the bold, controversial vision championed by a small but vocal group of researchers who argue we've been misreading the universe's blueprint for decades. At its core, the electric universe theory claims electromagnetism, not gravity, is the dominant force driving cosmic structure. Proponents point to the ubiquity of plasma, the fourth state of matter, a superheated soup of charged particles that makes up most of the visible universe. From the fiery tendrils of solar flares to the vast filaments connecting galaxy clusters, they see evidence of electric currents operating on scales mainstream science underestimates. Take galaxies. Conventional models rely on dark matter to explain their rotation, but electric universe advocates suggest the motion could be powered by colossal magnetic fields and interstellar currents instead. The theory's most radical stance, a flat rejection of the Big Bang. Instead of an explosive origin, the plasma universe posits an eternal, dynamic cosmos where new matter continuously forms through immense electrical discharges called Z-pinches. These cosmic lightning bolts, they argue, could birth stars and galaxies without the need for dark energy or inflation. Some even suggest celestial bodies like comets aren't icy leftovers from the solar system's formation, but charged objects discharging electricity as they travel, a claim that flies in the face of missions like Rosetta, which found comet surfaces rich in organic molecules, not electrical activity. Mainstream science dismisses the electric universe for a litany of reasons. First, while electromagnetism is powerful, its influence weakens dramatically over distance compared to gravity. The Moon orbits Earth not because of electric attraction but because of gravitational pull, a force that dominates at astronomical scales. Second, the cosmic microwave background, the redshift of galaxies, and the abundance of light elements all align with Big Bang predictions, leaving electric universe models scrambling to explain them without convoluted fixes. And then there's the math. General relativity and quantum field theory have made staggeringly precise predictions confirmed by experiments, while plasma universe proposals often lack rigorous mathematical frameworks. Yet the theory persists, fueled by a mix of genuine curiosity and deep skepticism toward institutional science. Its supporters, often outsider researchers or retired engineers, argue that cosmology has become too entrenched in untestable concepts like dark matter. They crave a simpler, more observable cosmos, one where celestial phenomena can be reproduced in plasma labs here on Earth. And while their ideas haven't gained traction in peer-reviewed journals, they've sparked lively debates online, challenging us to question whether we've overstated gravity's role or missed subtle electromagnetic clues woven into the fabric of space. Whether the electric universe is a revolutionary paradigm or a modern-day mirage, its existence underscores a vital truth: science thrives on dissent. Even fringe theories push us to test our assumptions, to demand better evidence, and to remember that the universe, in all its mystery, might still hold surprises no one has dared to imagine. The universe might not be a one-time event, but an endless dance of destruction and rebirth. Enter the cyclic model, a mesmerizing twist on cosmic origins where the Big Bang isn't the beginning, just the latest chapter in an infinite loop of expansion and collapse. Imagine the cosmos as a cosmic lung, breathing in and out over trillions of years, each exhale a fiery Big Bang, each inhale a crushing Big Crunch. It's a poetic vision that sidesteps the awkward question of what came before by declaring there was no before, only an eternal cycle. This idea isn't new. Early 20th century physicists like Alexander Friedmann toyed with oscillating universes, but modern versions, supercharged by string theory and brain cosmology, have given it startling new life. Picture our universe as a three-dimensional brain floating in a higher dimensional space, occasionally colliding with a neighboring brain. These collisions could unleash enough energy to mimic a Big Bang, resetting the cosmic clock without erasing the past entirely. Some models even suggest gravitational waves from previous cycles might still ripple through space-time, waiting to be detected. But there's a catch: entropy. The second law of thermodynamics insists that disorder always increases, meaning each cycle should grow messier than the last, like a photocopy of a photocopy. Eventually, the universe would devolve into a lukewarm haze of particles unable to rebound. Cyclic models counter this by proposing that entropy resets during the contraction phase, or that expansion dilutes it enough to make each new cycle viable. Critics argue these fixes are speculative, relying on physics far beyond current understanding. Others point out that observed dark energy, the force accelerating expansion, seems to doom the universe to endless stretching, not contraction. Yet the cyclic model lingers, tantalizing in its elegance. It solves puzzles like the universe's improbable initial smoothness by suggesting it was preconditioned by earlier cycles. And philosophically, it offers comfort: no definitive end, just transformation. Whether it's testable remains uncertain, but the mere possibility reminds us that our cosmic story might be far grander and stranger than we've dared to dream. What if our universe, with all its vast three-dimensional splendor, is nothing more than an illusion? A breathtakingly detailed hologram projected from a flat, two-dimensional surface. That's the mind-bending premise of the holographic principle, a theory that blurs the line between reality and cosmic sleight of hand. Born from the clash of quantum mechanics and black hole physics, this idea suggests that everything we experience, every star, every galaxy, even our own thoughts, might be encoded on a distant, unimaginably thin boundary, like a movie playing on the surface of an invisible screen. The roots of this radical notion trace back to the 1990s, when physicists Gerard T. Hooft and Leonard Susskind grappled with a paradox that threatened to unravel our understanding of black holes. According to quantum mechanics, information can never be destroyed, yet when matter falls into a black hole, it seemingly vanishes without a trace. The solution: imagine the black hole's event horizon, the point of no return, as a vast storage device. Every particle swallowed doesn't disappear, but is instead painted onto this surface like data etched onto a cosmic hard drive. The mind-blowing implication: the three-dimensional space inside the black hole could be entirely reconstructed from the information encoded on its two-dimensional boundary. From there, the leap to the holographic principle was inevitable. If a black hole's interior can be described by its surface, why not the entire universe? String theorists like Juan Maldacena took this further, showing mathematically that a higher dimensional space could indeed be equivalent to a lower dimensional one, like a hologram, where a flat image creates the illusion of depth. In this view, our universe might be a projection from a distant two-dimensional shell, with every event, every particle collision, every whisper of starlight merely shadows cast by processes happening on that faraway surface. The implications are staggering. If true, the holographic principle would mean that space itself is an emergent property, not fundamental, a collective hallucination woven from quantum entanglement. It could unite relativity and quantum mechanics, two pillars of physics currently at odds, by revealing space-time as a kind of quantum error-correcting code. Even time might lose its status as a fixed arrow, emerging instead from the interactions of underlying bits of information. Critics argue the theory is speculative, a mathematical curiosity without direct evidence. Yet tantalizing clues exist. Some versions predict subtle quantum jitters in the fabric of space, potentially detectable by future gravity wave observatories. Others suggest that the cosmic microwave background might bear faint imprints of this holographic structure, like fingerprints left on a projector lens. Whether the universe is truly a hologram or not, the holographic principle forces us to confront a profound question. What is reality if not what we perceive? It's a reminder that the cosmos might be far stranger, far more intricate than our senses or even our most advanced instruments can yet grasp. And that's the beauty of theoretical physics. It doesn't just reveal the universe's secrets, it redefines what secrets are left to uncover. What if nothing around us is real, not the stars, not the earth, not even the sensation of touch? The simulation hypothesis dares to suggest exactly that. Our universe might be an impossibly intricate digital construct, an ancestor simulation run by an advanced civilization to study their past or entertain themselves. Philosopher Nick Bostrom laid out this unnerving possibility in 2003 with a disarmingly simple trilemma. Either civilizations like ours almost always go extinct before developing simulation technology, or they almost never choose to run ancestor simulations, or we're almost certainly living in one right now. Bostrom's argument hinges on computing power. If civilizations survive long enough to create simulations indistinguishable from reality, and if they have any interest in running them, the number of simulated minds would vastly outnumber biological ones. Statistically, the odds favor us being among the simulations. The idea isn't entirely sci-fi. Tech mogul Elon Musk and astrophysicist Neil deGrasse Tyson have publicly entertained it, while quantum physicist Silas Bean proposed potential glitches in simulated physics, like subtle energy cutoffs in cosmic rays that might reveal pixel-like limits to our reality. But is the hypothesis science or metaphysics? Critics point out it's unfalsifiable, like solipsism. It's impossible to disprove, making it more philosophy than physics. Others argue it's a god of the gaps theory, invoking unseen programmers to explain mysteries like quantum indeterminacy or dark matter. Yet some scientists take it seriously enough to seek tests. One approach looks for computational shortcuts. If the universe is rendered like a video game, energy might be conserved by calculating only what's observed, leaving telltale statistical noise in high-energy particle experiments. Another probes for geometric anomalies in space-time, hunting for evidence the cosmos is built on a discrete lattice rather than smooth continuum. The simulation hypothesis also collides with uncomfortable existential questions. If we're simulations, do our choices matter? Could the simulation ever be shut off? Some dismiss it as postmodern nihilism, while others, like philosopher David Chalmers, suggest it doesn't change much. Simulated pain still hurts, simulated love still binds us. What makes the idea so persistent isn't just its eerie plausibility, but its audacity to reframe reality itself. In a cosmos where black holes warp time and particles teleport, why couldn't existence be code? Whether metaphor or menace, the hypothesis forces us to confront how little we truly know about the nature of being and how vast the possibilities still are. What if every decision you've ever made, every path taken or not taken, spawned an entirely new universe? That's the spine-tingling promise of the multiverse theory, a concept that stretches the fabric of reality to its breaking point. Imagine not just one cosmos, but an infinite tapestry of parallel worlds, each vibrating with its own unique history, physics, and even versions of you. Somewhere out there, a universe exists where dinosaurs never went extinct, where the Roman Empire never fell, or where you chose that other job, that other life. It's a dizzying thought, but is it science or philosophy? The idea isn't monolithic. It splinters into three mesmerizing variants, each with its own flavor of cosmic extravagance. First, the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in the 1950s. Here, every quantum event, every particle's random choice branches reality like a fork in an endless road. Schrödinger's cat isn't just alive or dead. Both outcomes happen, just in separate, non-communicating universes. Proponents argue this solves quantum weirdness by removing the need for observers to collapse probabilities into single outcomes. Skeptics, though, counter that it's ontologically extravagant, multiplying universes beyond necessity without a shred of direct evidence. Then there's the bubble universe model, rooted in cosmic inflation theory. Picture our universe as one frothy bubble in a vast, seething cosmic foam. Each bubble nucleates with its own laws of physics, some with stronger gravity, others with no electrons or even no atoms at all. This version finds traction because inflation, a leading explanation for the Big Bang's aftermath, naturally predicts such bubble formation. But here's the catch: these bubbles lie beyond our cosmic horizon, forever out of reach. We can't see them, touch them, or confirm they exist. Does that make the theory untestable or just waiting for a clever experiment? String theory cranks the multiverse up to 11, literally. Its landscape posits a staggering 10 to the 500 possible vacuum states, each representing a unique universe with its own constants. Why does our cosmos have just the right gravity, the right dark energy to allow life? In this view, it's pure luck we're just one lottery winner in a sea of failed tickets. Nobel laureate Steven Weinberg dubbed this the Anthropic Principle, but critics like physicist Paul Steinhardt call it a surrender, swapping predictive science for a postmodern shrug. The debate rages because the multiverse straddles the line between profound insight and unfalsifiable speculation. Without observable evidence, does it belong in physics or metaphysics? Some propose hunting for bruises in the cosmic microwave background, scars from ancient collisions with other bubble universes. Others suggest quantum entanglement might hint at parallel realities. But until then, the multiverse remains a tantalizing what-if, a mirror held up to our deepest questions about existence. Are we the sole marvel of the cosmos, or just one whisper in an infinite chorus? The answer, for now, lies somewhere beyond the edges of imagination. Long before telescopes peered into deep space or equations described the Big Bang, humanity turned to sacred texts and spiritual wisdom to explain the cosmos. Creationist cosmology offers a profoundly different origin story, one where the universe isn't the result of random physics but the deliberate act of a divine creator. From the poetic verses of Genesis to the intricate cosmologies of Hinduism and indigenous traditions, these narratives weave a tapestry of meaning, purpose, and intentional design. Yet when these beliefs collide with modern science, like the claim that Earth is only 6,000 years old, the debate ignites with questions about evidence, interpretation, and the very nature of truth. Take young Earth creationism, perhaps the most controversial strain of this thinking. Rooted in a literal reading of biblical genealogies, it posits that the entire universe was fashioned in 6 24-hour days roughly 6,000 years ago. Proponents point to perceived flaws in radiometric dating, arguing that decay rates might have shifted over time or that fossil layers were scrambled by Noah's flood. Organizations like Answers in Genesis even built the Ark Encounter, a life-sized replica of Noah's vessel, as a tangible rebuttal to mainstream geology. Scientists, however, dismantle these claims point by point. Radiometric dating isn't a single method but a web of cross-check techniques: uranium lead, potassium argon, carbon-14, all converging on Earth's 4.5 billion year age. Glaciers, with their meticulously counted ice layers, chronicle nearly 800,000 years of climate history, uninterrupted by any global deluge. And the light from distant galaxies, traveling millions of years to reach us, it's a silent witness to a cosmos far older than any literal scripture allows. Yet the conflict isn't just about dates or fossils, it's about epistemology, how we know what we know. Science relies on testable, repeatable evidence. Faith often transcends empiricism, valuing revelation and tradition. Some theologians, like those behind the Biologos Foundation, bridge the divide, viewing Genesis as allegory, a spiritual truth clothed in ancient cosmology, not a scientific manual. Others, like Intelligent Design Advocates, sidestep scripture altogether, arguing that life's complexity implies a designer, though critics retort that this merely dresses creationism in scientific jargon. What makes this debate so enduring isn't just clashing facts but clashing worldviews. For some, a universe without divine intent feels barren. For others, a world limited by dogma seems stifling. Yet between the poles, dialogues emerge. Jesuit astronomers scan the stars from Vatican observatories, while evolutionary biologists like Francis Collins, a devout Christian, see no contradiction between faith and science. Perhaps the real lesson isn't about choosing sides, but recognizing that the hunger to understand our origins, whether through prayer or particle accelerators, is what makes us human. And in that shared curiosity, there's more common ground than we might think. Picture the birth of our universe not as a fiery explosion, but as a silent, titanic collision, a glancing blow between two unfathomably vast cosmic membranes drifting through higher dimensional space. This is the ekpyrotic universe, a theory that swaps the Big Bang's singularity for an elegant ballet of colliding brains, weaving cycles of destruction and renewal into the fabric of reality itself. Rooted in string theory's mind-bending mathematics, the model suggests our three-dimensional universe is just one slice, a brain, floating in a hidden dimension, occasionally smashing into a neighboring brain with enough force to reset cosmic history. The name ekpyrotic comes from the ancient Greek word for conflagration, but unlike the Big Bang's chaotic inferno, this version of creation is startlingly orderly. When brains collide, their kinetic energy transforms into the searing plasma of particles and radiation we recognize as the Big Bang's aftermath, but without the baffling initial singularity. Even more striking, the model naturally explains the universe's puzzling uniformity. Before the collision, the brains stretch and smooth themselves over eons, erasing irregularities so that when they meet, the resulting cosmos emerges perfectly balanced, no inflationary period required. How does this differ from other cyclic models? The classic Big Bounce relies on gravity reversing cosmic expansion into a crunch, but it struggles with entropy, the buildup of disorder that should leave each cycle more chaotic than the last. The ekpyrotic universe sidesteps this by outsourcing the reset to brains in higher dimensions, where entropy from previous cycles effectively slides off the collision surface, preserving cosmic order. It's like pressing a cosmic reset button that doesn't carry over the chaos from the last game. String theorists love the elegance of this framework, but challenges remain. The brains themselves and the extra dimensions they inhabit are purely hypothetical, beyond current detection. Critics argue the model leans too heavily on untested physics, while others question whether brain collisions could really generate the observed patterns in the cosmic microwave background. And then there's dark energy. If the universe's expansion keeps accelerating, how could brains ever draw close enough to collide again? Some versions propose hidden forces tugging brains together, but these tweaks risk feeling like ad hoc fixes. Yet the ekpyrotic universe endures as a tantalizing what-if. It merges the cyclical beauty of ancient cosmology with cutting-edge physics, offering a vision where the universe isn't born from nothing, but from something, a tangible, almost tactile event in a grander multidimensional arena. Whether it's the true story of our origins or just another stepping stone toward deeper understanding, it reminds us that the cosmos might not just be stranger than we imagine, but stranger than we can imagine. And that's where the real adventure begins. What if the universe doesn't end with a whimper or a bang, but with a silent transformation into the next cosmic cycle? That's the breathtaking premise of conformal cyclic cosmology, Roger Penrose's daring vision of an infinite, self-renewing cosmos where the far future of one universe becomes the Big Bang of the next. Forget fiery collisions or oscillating brains. This theory hinges on the subtle physics of entropy and the eerie symmetries of spacetime itself, rewriting the rules of cosmic rebirth in a way only a mind like Penrose's could conceive. At its heart is a deceptively simple observation. As the universe expands toward heat death, all matter eventually decays into massless particles like photons, and black holes evaporate into radiation via Hawking radiation. In this distant, frozen era, the distinction between past and future blurs. Space becomes smooth and featureless, devoid of scales or landmarks, a state Penrose calls conformally invariant. Strikingly, this late-time emptiness mathematically mirrors the ultra-smooth, low-entropy conditions of the early universe. The radical leap, these two states aren't just similar, they are identical. The end of one cycle is the beginning of another, with no boundary between them, like a Möbius strip of cosmic time. Penrose's theory makes one jaw-dropping prediction. Traces of earlier universes might linger in our own. As black holes from past cycles evaporated, they'd release torrents of energy in their final moments. These bursts, Penrose argues, could imprint as faint, circular patterns on the cosmic microwave background, so-called Hawking points, named for his late colleague Stephen Hawking. In 2010, Penrose and collaborator Vark Gurzadian claimed to have spotted these very patterns in WMAP and Planck satellite data, sparking fierce debate. Mainstream cosmologists pushed back, arguing the anomalies could be statistical noise or artifacts of data processing. Yet the allure remains. If verified, these ghostly rings would be the first tangible evidence of a universe that came before ours. Critics highlight glaring challenges. The theory requires exotic physics to explain how all particles lose their mass in the far future, a process far beyond the standard model. Others question whether the conformal matching of future and past is mathematically rigorous or philosophically convenient. Even fans admit the idea is speculative but isn't all frontier science. What makes conformal cyclic cosmology so compelling isn't just its audacity, but its elegance. It sidesteps the need for a singularity or unexplained inflation, weaving the universe's death into its rebirth with haunting symmetry. Whether Hawking points prove real or not, Penrose's vision forces us to confront profound questions. Is time truly linear or just a cycle we perceive in fragments? Could the cosmos be less a one-time drama than an eternal echo, reverberating through epochs we can scarcely imagine? In a field obsessed with beginnings, Penrose dares to ask, what if the end is just another name for the start? What if the Big Bang wasn't just the beginning of space, but the moment time itself flipped direction? This is the startling premise of time reversal theories, which suggest the arrow of time might have pointed backward before the universe's fiery birth. Imagine a cosmic hourglass. On one side, entropy increases toward the future as we know it. On the other, entropy decreases as time flows backward toward the singularity. It's a concept that twists our intuition into knots, yet emerging research in quantum gravity hints that such a temporal U-turn might not just be possible, it could solve some of cosmology's deepest puzzles. The idea builds on a curious symmetry in physics. At the microscopic level, most equations work perfectly whether time runs forward or backward. Yet our macroscopic experience is tyrannically one-directional. Eggs don't unscramble and coffee never unstirs itself. This irreversibility stems from entropy, the universe's tendency toward disorder, which always increases, or so we thought. Quantum gravity researchers like Julian Barber and Stefan Alexander propose that at the extreme densities of the Big Bang, entropy might have been at its peak, not its minimum. In this view, time didn't emerge from nothing. It reversed, creating the illusion of a beginning as the universe bounced from a previous collapsing phase. Supporters point to tantalizing mathematical hints. Loop quantum gravity, a leading candidate for unifying quantum mechanics and relativity, allows solutions where time's arrow flips at high energies. Some interpretations of the Wheeler-DeWitt equation, a cornerstone of quantum cosmology, even describe a universe without time at all, where past and future are emergent properties, not fundamentals. If true, the Big Bang becomes less a creation event and more a cosmic pivot, a moment where time's flow inverted like a river doubling back on itself. But the theory isn't without paradoxes. If time ran backward before the bang does before even make sense, language stumbles here, trapped by linear thinking. Critics argue that reversed time is a mathematical abstraction with no observable consequences after all. Any information from a pre-bang era would be scrambled beyond recognition by the singularity's chaos. Others contend that entropy can't simply reset. The universe's low entropy starting point remains its most inexplicable feature, whether time reversed or not. Yet the boldest thinkers press forward. If time reversal is real, it could explain why the universe appears so finely tuned for life. A symmetrical temporal structure might naturally produce the orderly conditions we observe, no inflationary magic required. It's a radical reimagining of causality itself, where the future influences the past as much as the past shapes the future. Whether this vision survives scrutiny or collapses under its own weight, it reminds us that in the quantum realm, even time might be more fluid and more mysterious than we ever dared to assume. Here's a mind-bending twist. What if our entire universe isn't expanding into endless space, but trapped inside the crushing depths of a black hole? Black hole cosmology flips the script on cosmic origins, suggesting that the Big Bang wasn't the birth of space and time, but the moment our reality formed within the singularity of a far larger, higher-dimensional black hole. It's a theory that merges the most extreme scales of physics, from the infinitely small to the unimaginably vast, into a single, startling narrative. The idea gains traction from eerie similarities between black holes and the early universe. Both feature singularities, points of infinite density where the known laws of physics break down. Both warp spacetime so severely that time and space swap roles at their boundaries, and both are surrounded by horizons, the event horizon for a black hole, the cosmic horizon for our observable universe. Some physicists argue these parallels aren't coincidental. If you mathematically model the collapse of a star into a black hole and run the equations backward, you get something that looks suspiciously like an expanding universe. Could the Big Bang, then, have been the white hole eruption of matter and energy from a parent black hole's singularity? This isn't just poetic symmetry, it's grounded in cutting-edge theoretical work. Loop quantum gravity, for instance, avoids singularities by predicting bounces where collapsing matter rebounds into expansion. If our universe originated from such a bounce inside a black hole, it would explain the low entropy of the early cosmos. The black hole's horizon naturally sorts matter into an orderly state as it forms. Even more intriguing is the holographic principle's role here. If a black hole's interior can be entirely described by information encoded on its surface, perhaps our universe, too, is a holographic projection from the boundary of some greater cosmic structure. Critics highlight glaring gaps. For one, black holes in our universe don't seem to spawn new universes, they devour matter, not spew it out. The theory also struggles to explain dark energy or the precise uniformity of the cosmic microwave background without invoking additional mechanisms. And then there's the elephant in the room. If we're inside a black hole, what lies outside? The answer might require physics beyond our current grasp, like string theory's higher dimensions or the multiverse's infinite nesting dolls of reality. Yet the theory's boldness is its strength. It reframes the existential dread of black holes objects synonymous with annihilation as potential cradles of creation. It suggests that time and space might be local phenomena, artifacts of our particular cosmic prison rather than fundamental truths. And it offers a hauntingly beautiful vision of cosmic recursion. Every black hole a potential universe, every universe potentially filled with black holes of its own, birthing new realities in an endless fractal cascade. Whether black hole cosmology is a profound insight or a provocative thought experiment, it forces us to confront the limits of our knowledge. If true, it means the darkest objects in the cosmos aren't just destroyers. They're the architects of existence itself. And that realization might be the key to unlocking the greatest mystery of all. Not just where we came from, but what else might be out there, hidden beyond the event horizon of our understanding. Imagine a universe popping into existence from pure nothingness. No energy, no matter, just the silent hum of empty space. That's the radical promise of the quantum fluctuation origin theory, a mind-bending idea that suggests our entire cosmos could be the ultimate free lunch, born from a random flicker in the quantum void. At the heart of this concept lies one of physics' most bizarre truths. There's no such thing as truly empty space. Even in a perfect vacuum, particles blink in and out of existence like cosmic fireflies, dancing on the edge of reality itself. These are virtual particles, ephemeral pairs of matter and antimatter that borrow energy from the vacuum just long enough to exist before annihilating each other, all within the span of a heartbeat too brief to measure. But what if, instead of vanishing back into nothingness, one of these quantum fluctuations didn't cancel out? What if it ballooned outward, inflating faster than it could repay its energy debt? Under the right conditions we still don't fully grasp, that tiny blip could stretch into an entire universe. It's a notion championed by physicists like Tryon in the 1970s, who first proposed that our cosmos might be a long-lived quantum fluctuation, a statistical outlier in an endless sea of nothingness. The math is staggering. In a vacuum teeming with quantum activity, given enough time, and time itself might be infinite, even the most improbable event becomes inevitable. Given eternity, a universe like ours isn't just possible, it's unavoidable. This theory elegantly sidesteps the need for a singularity or divine spark. Instead, it leans on quantum field theory, where the vacuum isn't passive but seethes with potential, a roiling foam of probabilities. Some interpretations even suggest our universe's total energy might sum to zero, the positive energy of matter and radiation perfectly balanced by the negative energy of gravity. If true, creation wouldn't require any net energy at all, just a fleeting imbalance in the quantum books. Yet the idea isn't without its paradoxes. Quantum fluctuations typically operate on microscopic scales, so how could one scale up to cosmic proportions? One answer lies in inflation, the same exponential expansion thought to have shaped the early universe. A random quantum jump, amplified by inflation's hyper-stretching of spacetime, could theoretically seed an entire cosmos. But critics argue this just kicks the can down the road. What triggered inflation? And why does the quantum vacuum have these properties in the first place? The deeper question, though, is philosophical. Can something really come from nothing? Physicists like Lawrence Krauss argue that nothing is a misnomer. The quantum vacuum with its latent fields and energies is a far cry from classical nothingness. Others retort that this redefines the problem rather than solving it. Regardless, the quantum fluctuation origin forces us to confront the unsettling possibility that existence itself might be a statistical fluke, a cosmic accident in an eternal void where universes rise and fade like bubbles in a boiling pot. Whether it's the final answer or just a stepping stone, this theory reshapes our understanding of nothingness. The vacuum isn't empty, it's pregnant with potential, a canvas where reality flickers in and out of being. And if our universe is just one ripple in that infinite dark, what else might be flickering into life beyond the edges of our perception? The answer, for now, remains hidden in the quantum shadows. Einstein once called it his greatest blunder, but what if he was right all along? The story of the static universe model begins with a cosmic puzzle that plagued early 20th century astronomers. If gravity pulls everything inward, why doesn't the universe collapse under its own weight? Einstein's solution was elegant yet controversial, a mathematical fudge factor he called the cosmological constant, a repulsive force woven into the fabric of space-time itself to balance gravity's tug and keep the universe eternally unchanging. It was a bold fix for what seemed like a stable, eternal cosmos, until Edwin Hubble's observations in the 1920s shattered that illusion, revealing galaxies racing away from each other in an expanding universe. Einstein discarded his constant, dismissing it as unnecessary. Yet irony has a way of circling back. Nearly 70 years later, astronomers made a discovery that would resurrect Einstein's blunder in spectacular fashion. Observations of distant supernovas showed the universe wasn't just expanding, it was accelerating as if pushed by some unseen repulsive force, the culprit. Dark energy, a mysterious phenomenon that behaves uncannily like Einstein's long-abandoned cosmological constant. Suddenly, that old mathematical placeholder didn't seem so foolish after all. Modern cosmology now sees the constant as a potential key to dark energy's identity. Quantum field theory suggests empty space isn't truly empty. It crackles with vacuum energy, a background hum of particle-antiparticle pairs flickering in and out of existence. If this energy exerts negative pressure, it could explain cosmic acceleration, effectively making Einstein's constant a natural feature of space-time rather than an arbitrary add-on. But the plot thickens. Calculations of vacuum energy's strength overshoot observed dark energy by a staggering 120 orders of magnitude. This worst prediction in physics hints either at a fundamental misunderstanding or the need for exotic explanations, like dynamic fields that evolve over time. The debate forces us to confront profound questions. Was Einstein's instinct about a static universe wrong or just premature? Could the cosmological constant be a bridge between quantum mechanics and gravity, two theories still stubbornly at odds? Whatever the answer, the story is a humbling reminder even geniuses can't always foresee how their ideas might echo through time. Sometimes the universe keeps secrets not just in its vastness, but in the twists and turns of scientific history itself. Imagine a force so potent it doesn't just push galaxies apart. It shreds the very fabric of reality, atom by atom, until existence itself dissolves into chaos. That's the apocalyptic vision of phantom energy, a theoretical variant of dark energy so extreme it could one day rip spacetime apart in an event cosmologists call the Big Rip. Unlike the gradual heat death of traditional dark energy scenarios, this theory offers a far more violent finale for the cosmos, where even atomic bonds and the particles within them are torn asunder by the universe's runaway expansion. At the heart of this harrowing idea is dark energy's equation of state, a measure of how its pressure relates to its energy density. In standard models, dark energy acts like a gentle but relentless force, represented by a value called W, which hovers around -1. But phantom energy dials this up to nightmarish levels, with W plummeting below -1. This tiny numerical tweak might seem innocuous, but its implications are catastrophic. As space stretches faster than light can traverse it, structures bound by gravity, galaxies, stars, planets, would be ripped apart first. Next, the electromagnetic forces holding atoms together would fail. Then even atomic nuclei would disintegrate. Finally, in the last inconceivable moment, space-time itself would rupture, leaving behind nothing. No particles, no dimensions, no remnants, just a featureless void where the universe once was. Observational data, however, paints a less dramatic picture. Measurements of distant supernova, galaxy clusters, and the cosmic microwave background consistently peg dark energies W close to -1 with only slight deviations. The European Space Agency's Planck satellite, for instance, constrains W to around -1.03, plus or minus a hair's breadth. That's nowhere near the phantom energy threshold needed for a big rip. Yet the theory lingers in the scientific imagination because it exposes the fragility of our cosmic assumptions. What if dark energy evolves over time? Could its strength increase as the universe ages, inching us toward dissolution? Some speculative models suggest phantom energy could emerge from exotic quantum fields or higher dimensional physics, where the vacuum of space behaves unpredictably at extreme scales. Others argue it's a mathematical curiosity with no basis in reality, a ghost in the equations rather than a genuine threat. But the mere possibility forces us to confront how little we truly understand about dark energy. Is it a constant, immutable property of space, as Einstein's cosmological constant suggests? Or is it a dynamic entity capable of shifting into something far more sinister? The Big Rip might never happen, but its specter haunts cosmology as a reminder of the universe's capacity for surprises. After all, if we've learned anything from cosmic history, it's that the universe rarely adheres to our expectations. Whether it ends with a whimper, a bang, or a rip, one thing is certain: the final chapter of reality will be written by forces we're only beginning to fathom. Supersymmetry once promised to be the universe's missing puzzle piece, an elegant theory that could unite all fundamental forces and explain the very fabric of reality. At its core lies a simple but radical idea. For every known particle in the Standard Model, there exists a hidden, heavier twin. Electrons would have selectrons, quarks would have squarks, and photons would have photinos. These sparticles, as theorists call them, would balance the quantum books, solving mysteries like dark matter's identity and the unnaturally small mass of the Higgs boson. But here's the catch: despite decades of searching, not a single supersymmetric particle has been found. The dream of a supersymmetric universe, once the darling of theoretical physics, now teeters on the edge of crisis, and its potential role in cosmic origins hangs in the balance. The theory's allure lies in its mathematical beauty. Supersymmetry smooths out the jagged edges of particle physics, eliminating the infinities that plague quantum field theory calculations. It also offers a compelling dark matter candidate, the lightest supersymmetric particle, or LSP, which could silently pervade the cosmos, invisible yet shaping galaxies with its gravitational pull. Most tantalizingly, it might explain why the universe's expansion accelerated so dramatically after the Big Bang. Some models suggest particles could have influenced inflation, that brief but pivotal moment when the cosmos ballooned from subatomic size to macroscopic scales in a fraction of a second. If true, supersymmetry wouldn't just describe particles, it would rewrite our origin story. Yet the Large Hadron Collider, humanity's most powerful microscope, has delivered crushing disappointment. Designed partly to uncover particles, the LHC has instead found empty shells where supersymmetry's predictions once stood. The machine's collisions, reaching energies once thought certain to reveal at least the lightest particles, have produced nothing but ordinary particles and mounting frustration. Critics argue the theory's proponents keep moving the goalposts, adjusting parameters to push particle masses beyond detection limits. What began as a tight framework now feels like a fading hope, its elegance buckling under the weight of negative data. This leaves cosmology at a crossroads. If supersymmetry fails, what fills the void? Some theorists turn to alternative ideas like extra dimensions or string theory's vast landscape. Others double down, suggesting sparticles might still lurk just beyond our current energy reach, waiting for a next-generation collider. But with each passing year, the supersymmetric universe grows harder to defend, not because it isn't beautiful, but because the universe itself seems indifferent to our desire for symmetry. Whether this marks the end of an era or just a temporary setback, one thing is clear. The cosmos owes us no favors, and the truth, however messy, lies where the evidence leads. What if the only conscious mind in the entire universe isn't yours or even human, but a lone, disembodied brain that's spontaneously assembled from random quantum fluctuations, complete with false memories of reading this very sentence? That's the unsettling premise of the Boltzmann brain paradox. A thought experiment so bizarre it forces us to question not just the nature of reality, but the reliability of our own existence. Named after 19th-century physicist Ludwig Boltzmann, who first grappled with how order emerges from chaos, the idea takes his statistical mechanics to its logical extreme. In an endless universe governed by probability, even the most improbable events must happen eventually, including the random formation of a fully self-aware mind. Picture an infinite, lifeless cosmos trillions of years into its heat death, where particles drift in cold, featureless darkness. Given enough time, those particles could randomly arrange themselves into any configuration, even one that perfectly mimics a functioning human brain. Not attached to a body, not nourished by blood, just a flickering moment of consciousness conjured from the void, complete with fabricated sensory input. How would this Boltzmann brain know it wasn't real? Every memory, every perception of the external world would be an illusion generated by its accidental structure. And if such brains outnumbered genuine observers like us, statistical inevitability in a vast, chaotic universe, then the odds suggest we might be the illusions. The implications are dizzying. If consciousness can emerge from random fluctuations, then the orderly universe we perceive could be a fantasy stitched together by a malfunctioning Boltzmann brain hallucinating its own past. This isn't just sci-fi speculation, it's a legitimate crisis in cosmology. The paradox arises because our current understanding of entropy suggests low-probability ordered states like brains should occasionally pop into existence if you wait long enough, making them far more likely than the immense complexity of an entire 13.8 billion-year cosmic history. Modern physics recoils at the idea, with most theorists rejecting it as absurd. Sean Carroll famously quipped that if your theory predicts you're probably a Boltzmann brain, it's a sign your theory is catastrophically wrong. Yet the problem refuses to die. Some propose solutions involving cosmological boundaries, like a finite universe that doesn't allow infinite time for fluctuations. Others suggest consciousness might require more than just particle arrangements, invoking unknown physics that prevents disembodied minds. But the deepest lesson here isn't about brains at all, it's about how statistical reasoning collides with human intuition. Reality might not owe us coherence, and the universe's strangest truths could lurk where logic and improbability meet. Whether a cautionary tale or a genuine paradox, the Boltzmann brain forces us to confront how little we truly understand about observation, existence, and the fragile line between mind and cosmos. While black holes devour everything in their path, white holes would be their cosmic opposites, objects that can only expel matter and energy, never absorb them. Think of them as the universe's fire hydrants, spewing out light and particles with unstoppable force, reversing the known laws of black hole physics. Some theorists propose these enigmatic objects aren't just hypothetical quirks of mathematics, but could be the very birthplaces of new universes, including our own. Picture a white hole as the Big Bang's cosmic twin, a singularity erupting outward, flooding space-time with the raw ingredients of existence instead of swallowing them whole. The idea emerges from Einstein's field equations, which, when run backward in time, mathematically permit white holes as valid solutions. Just as a black hole's event horizon marks a point of no return for infalling matter, a white hole's horizon would be an exit door nothing can re-enter. Some models even suggest a black hole's interior could connect to a white hole in another universe, forming an Einstein-Rosen bridge, a wormhole stitching together separate cosmic realities. In this scenario, matter vanishing into a black hole in one cosmos might re-emerge as the Big Bang of another, turning black holes into cosmic recyclers and white holes into creators. But there's a glaring problem. No white hole has ever been observed. Unlike black holes, which reveal themselves through gravitational effects and radiation, white holes would be inherently unstable. Any infalling matter, even a single hydrogen atom, would theoretically collapse the white hole into a black hole, sealing its fate. Some physicists argue that if white holes exist at all, they'd be fleeting, vanishing moments after forming, like bubbles bursting in a quantum foam. Others speculate they might lurk in the distant past, disguised as the Big Bang itself, an initial explosion of energy with no prior cause, only aftermath. The theory's biggest hurdle is entropy. Black holes obey the second law of thermodynamics, their horizons ensuring disorder always increases. White holes, by contrast, appear to violate this principle by spewing out low entropy, highly ordered energy, like a broken dam releasing a perfectly structured tidal wave. Reconciling this with known physics would require radical revisions, perhaps involving quantum gravity or undiscovered symmetries in spacetime. For now, white hole cosmology remains a tantalizing what-if, a reminder that the universe's greatest mysteries might hide not in the darkness of black holes, but in the blinding light of their theoretical counterparts. Whether they're cosmic phantoms or the seeds of reality itself, white holes challenge us to rethink the boundaries of creation, and whether beginnings and endings are just two sides of the same cosmic coin. Black holes might symbolize cosmic endings, but what if our entire universe is the result of a previous universe's collapse? A cosmic phoenix rising from the ashes of a singularity. That's the daring vision of bouncing cosmology, a theory that replaces the Big Bang's fiery birth with an elegant rebound, a universe that collapses inward only to spring back outward over and over in an endless cycle of renewal. Instead of a singular, inexplicable moment of creation, this model suggests our cosmos is just the latest iteration in an infinite sequence, each bounce wiping the slate clean while preserving subtle echoes of the past. At the heart of this idea lies a radical reimagining of gravity's behavior at the smallest scales. General relativity predicts that collapsing matter inevitably forms singularities, points of infinite density where spacetime itself breaks down. But many physicists suspect this is a sign that Einstein's theory is incomplete, failing to account for quantum effects that might prevent such extremes. Enter loop quantum gravity, a leading candidate for unifying quantum mechanics and relativity. In this framework, spacetime isn't smooth and continuous but woven from tiny, indivisible threads, a fabric so fine it can't be torn, only stretched and twisted. When matter collapses under gravity, these threads resist infinite compression, creating a repulsive force that halts the collapse and triggers a rebound. Picture a universe squeezed into a hyper-dense marble, only to bounce back with a vengeance, its stored energy exploding into a new expansion phase. This isn't just theoretical sleight of hand. Loop quantum cosmology, the application of these ideas to the universe as a whole, makes tangible predictions. Unlike the Big Bang's incomprehensible singularity, a bounce would leave traces in the cosmic microwave background, subtle imprints of the previous universe's structure. Some models even suggest that the universe's current large-scale uniformity isn't a fluke of inflation but a relic of pre-bounce smoothing, as gravitational forces erased irregularities during the contraction phase. It's as if the cosmos inherits a kind of memory, a thermodynamic reset that preserves order across cycles. But the theory isn't without hurdles. The biggest challenge is entropy, the universe's tendency toward disorder. If each cycle grows messier than the last, eventually the rebounds would fizzle out, leaving a lukewarm haze incapable of reigniting. Bouncing cosmologists counter that quantum effects might reset entropy at each bounce, or that the vast expansion phases dilute disorder enough to make each new cycle viable. Others propose that black holes evaporating via Hawking radiation could purge entropy from the system, acting as cosmic janitors between cycles. What makes bouncing cosmology so compelling isn't just its avoidance of singularities, it's the philosophical resonance. Ancient Hindu and Buddhist cosmologies envisioned cyclical time, and modern physics might be echoing those intuitions with equations. Whether the universe truly bounces or not, the idea invites us to see existence not as a one-time event, but as a stanza in an endless poem, each verse written with the ink of the last. And if the next bounce is already written into the fabric of reality, our universe's story might be far from over, just paused, waiting for the next act to begin. What if the speed of light, that cosmic speed limit etched into physics textbooks, wasn't always constant? The variable speed of light theory, or VSL, dares to rewrite one of Einstein's most sacred rules, suggesting that light's velocity might have been drastically different in the early universe. This isn't just a minor tweak to the equations. It's a seismic shift that could unravel some of cosmology's most stubborn mysteries without resorting to exotic fixes like inflation or dark energy. Imagine the universe's first moments, a seething cauldron of energy where the laws of physics as we know them hadn't yet settled into their current form. In this primordial chaos, light might have raced across space exponentially faster than its modern 300,000 kilometers per second. Proponents like physicist Joe Megiddo argue this faster speed could explain how distant regions of the cosmos appear so uniform, the so-called horizon problem, without invoking inflation's hyper-stretching of spacetime. If light traveled faster in the past, it could have zipped between far-flung areas, evening out temperatures before slowing to today's crawl. It's like solving a traffic jam not by widening the highway, but by letting cars temporarily break the speed limit. But why would light's speed change? Some VSL models tie it to the evolving properties of spacetime itself. In the intense heat of the early universe, the vacuum of space might have been less sticky, allowing photons to slip through with less resistance. Others suggest deeper modifications to relativity, where the constants we consider fixed, like c, are actually dynamic, evolving as the universe cools. These ideas aren't pulled from thin air. They're grounded in quantum gravity research, where spacetime's fabric is thought to fluctuate wildly at microscopic scales. If spacetime itself was frothier in the past, light's speed could have been as variable as a ship navigating turbulent seas. Mainstream cosmology, however, hasn't embraced VSL with open arms. Critics point to the mountain of evidence supporting relativity's constancy, from precision tests in particle accelerators to the flawless timing of pulsars. If C had changed, they argue, we'd see distortions in the cosmic microwave background or discrepancies in the fine structure, constant, a dimensionless number that hinges on light speed. So far, such anomalies remain elusive or contested. The most famous claim, a 1998 study suggesting shifts in the fine structure constant, was later met with skepticism as follow-up observations failed to confirm it. Yet the theory refuses to die, in part because it tackles problems inflation can't. Inflation requires a finely tuned, inflaton field with just the right properties to start and stop its exponential expansion, a field we've never detected. VSL, by contrast, offers a leaner solution, modifying known physics rather than inventing new entities. It also sidesteps the multiverse problem, where inflation's endless bubble universes render many predictions untestable. For some theorists, that's reason enough to keep VSL on the table, even as a provocative foil to orthodoxy. The debate crystallizes a deeper tension in science. Do we cling to elegant theories and patch their flaws, or tear up the rulebook when faced with contradictions? VSL's fate may hinge on upcoming observations like subtle ripples in gravitational waves from the early universe, which could carry imprints of light's primordial speed. Until then, it stands as a bold reminder that even the most sacrosanct laws might be open to revision. After all, if the universe teaches us anything, it's that change is the only true constant. Look closely at a fern's frond or a snowflake's delicate branches, and you'll notice something uncanny, the same patterns repeating at smaller and smaller scales, an endless hall of mirrors where every level reflects the whole. Now imagine that principle applied to the cosmos itself. The fractal universe theory proposes that the large-scale structure of reality isn't just clustered matter. It's an infinite cascade of self-similar forms where galaxies group into clusters, clusters into superclusters, and so on without end, like a cosmic Russian nesting doll. This isn't just poetic speculation. Galaxy surveys like the Sloan Digital Sky Survey reveal eerie hints of hierarchical organization. Vast filaments of galaxies weave through the cosmos, connected in web-like patterns that seem to echo across scales. Proponents point to mathematical models showing how gravity could sculpt matter into these recursive shapes, with density fluctuations in the early universe seeding structures that repeat like a fractal algorithm run amok. If true, it would mean the universe isn't just vast, it's endlessly nested with no true top or bottom level. But there's a problem: the cosmological principle. Modern cosmology rests on the assumption that, at grand scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction, with no privileged center or edge. Fractal patterns, by their nature, defy this uniformity. A truly fractal cosmos would grow lumpier the wider you zoomed out, contradicting the smoothness we see in the cosmic microwave background. Critics argue that while galaxy distributions show clustering, they eventually average out to homogeneity at scales beyond a few 100 million light-years. The debate hinges on interpretation. Are we seeing the faint edges of a fractal we can't yet measure, or is the apparent hierarchy just a transient phase in cosmic evolution? Some theorists bridge the gap with hybrid models. Perhaps the universe is quasi-fractal self-similar up to a point, then smoothing into homogeneity. Others suggest that dark matter's invisible scaffolding might create fractal-like imprints in visible matter without violating the cosmological principle. The most radical voices, though, question whether homogeneity is an illusion, a statistical artifact of our limited vantage point. After all, we're trapped in a tiny corner of an incomprehensibly vast expanse. Could our assumptions about the whole be as flawed as a goldfish generalizing about oceans based on its bowl? Whether fractal or flat, the theory pushes us to confront how deeply pattern-seeking instincts shape our cosmic narratives. The universe might not owe us symmetry, but that won't stop us from searching for it in the stars. What if the Big Bang wasn't the beginning of time, just a turning point in an endless cosmic cycle? Theories like loop quantum gravity offer a startling possibility. That time itself extends beyond the bang, bridging our universe to a previous epoch erased by that cataclysmic reset. Imagine time as a river flowing uphill before the bang, then cascading downhill into our expanding cosmos, a cosmic watershed moment where the arrow of time flipped direction but never truly started from nothing. Loop quantum gravity, a leading framework for unifying quantum mechanics and general relativity, paints spacetime not as smooth and continuous but as a fabric woven from indivisible threads. At the extreme densities of the Big Bang, these threads resist infinite compression, creating a quantum bounce where collapsing matter rebounds into expansion. In this view, our universe could be the aftermath of a previous cosmos that contracted to a near singularity before springing back to life. The equations suggest time didn't begin at the bang it transformed, carrying subtle imprints of its prior phase like echoes in a cave. But this raises a paradox sharper than any singularity: causality itself. If events before the bang influenced our universe, how can we reconcile cause and effect when time's arrow might have reversed or fractured? Some models propose that pre-bang time operated under different physical laws, with quantum entanglement threading connections across the bounce like invisible stitches. Others suggest causality is an emergent property, a local phenomenon that resets at each cosmic cycle. The most radical idea, that time is an illusion altogether, a byproduct of deeper, timeless quantum correlations we're only beginning to fathom. Critics argue these models stretch plausibility, trading one mystery, the bang's origin, for another, an unknowable prehistory, yet the allure persists. If time extends beyond the bang, it could explain the universe's improbable low-entropy starting point, not as a fluke, but as a natural legacy of pre-bounce smoothing. It's a vision both humbling and exhilarating, that our cosmos might be less a creation than a chapter in an infinite saga, where beginnings and endings are just bends in a river of time we've barely begun to navigate. What if life on Earth didn't begin here at all, but was planted deliberately by an intelligence so advanced their reach spans galaxies? This is the spine-tingling premise of cosmic panspermia, a theory that stretches the traditional idea of life hitching rides on comets into something far grander, an intentional universe-scale seeding program. Picture this: an ancient civilization, perhaps billions of years ahead of us, engineering microbial life to withstand the void of space and dispersing it like cosmic gardeners, ensuring life takes root wherever conditions allow. It's a concept that blurs the line between science and speculation, weaving together astrobiology, the Fermi paradox, and the unsettling possibility that we might be part of someone else's experiment. The classic panspermia hypothesis that life spread naturally via asteroids or interstellar dust already challenges Earth-centric origins. But the directed version takes it further, proposing that life's building blocks weren't just accidental stowaways but precision payloads. Consider the eerie complexity of DNA. Its 4-billion-year-old code is staggeringly robust, surviving extreme radiation and vacuum conditions in lab tests. Could such resilience be an engineered trait designed for interstellar travel? Some researchers point to the bacterium Deinococcus radiodurans, nicknamed Conan the Bacterium, for its ability to endure cosmic radiation doses that would shred human DNA. If microbes like this were deliberately fortified and dispersed, they might serve as universal life starters, awakening on habitable worlds like time capsules set by an unseen hand. This idea collides head-on with the Fermi paradox, the glaring silence where we'd expect alien chatter. If life is so easily spread, why haven't we found any evidence of these cosmic gardeners? One chilling answer: we are the evidence. Earth could be a wilderness preserve in a galactic zoo, or worse, a lab dish in a sprawling experiment. Alternatively, the Cedars might be long gone, their civilization vanished but their biological legacy thriving. Others argue the paradox isn't a paradox at all. If life is ubiquitous because of directed panspermia, advanced civilizations might be so common they're uninterested in contact, like humans rarely stopping to chat with ants. The theory's boldest claim: even the laws of physics might be engineered. Some variants suggest fine-tuning, the unnerving precision of constants like gravity or the strong nuclear force could reflect intentional calibration by a prior intelligence. Imagine a universe where the rules themselves are artifacts, tweaked to maximize the chances of life. It's a dizzying thought, rendering our search for natural explanations futile, like lab mice trying to deduce why their cage has exactly 12 food dispensers. Critics dismiss this as untestable mythology, a scientific dead end. Without artifacts, say, a microbe with unmistakable synthetic DNA, it's hard to falsify. Yet the questions linger. If we one day find life on Mars or Europa with DNA eerily similar to Earth's, how would we prove it wasn't contamination or deliberate planting? The irony is profound. The more we search for life's origins, the more we might uncover signs that we're not just discoverers, but the discovered. Whether cosmic gardening is fact or fiction, it forces us to confront a humbling possibility. Life might not be a solitary accident, but a cosmic inevitability, or worse, someone else's project. And if that's true, the universe isn't just stranger than we imagine. It might be stranger than we can imagine, with our very existence a single line in a biography written by minds beyond our comprehension. What if the universe doesn't exist until someone looks at it? This isn't just philosophical musing, it's the startling claim of quantum mechanics' observer effect, where particles seem to choose their state only when measured. Take the famous double-slit experiment. Fire electrons at a screen, and they behave like waves, creating an interference pattern. But the moment you place a detector to see which slit each electron passes through, they switch to acting like particles. It's as if reality itself hesitates until observed, a phenomenon even Einstein called spooky. Now, extrapolate that to the cosmic scale. If tiny particles depend on observation for definition, could the entire universe require consciousness to crystallize into existence? This idea, known as radical idealism or the consciousness-created universe, turns traditional cosmology on its head. Instead of matter giving rise to minds through evolution, minds might be the fundamental fabric shaping matter. Philosophers like George Berkeley argued this centuries ago, that reality is purely mental, with the material world an illusion. But today, quantum physics lends it eerie plausibility. The Copenhagen interpretation, one of quantum mechanics' oldest frameworks, suggests reality remains a haze of probabilities until observation collapses it into certainty. Push this to its extreme, and you get theories like the participatory anthropic principle, where conscious observers are necessary for the universe to manifest. Without them, it's all just math equations without substance. Critics, though, pounce on the slippery slope of solipsism. If consciousness creates reality, why do we all agree on shared experiences? Why doesn't a rock disappear when no one's looking? Defenders counter with quantum decoherence. Interactions with the environment act as constant observers, preventing macroscopic objects from flickering in and out of existence. Others propose a hierarchy of consciousness, with human minds just one layer in a cosmic web of perception. Even stars or black holes might possess rudimentary awareness in this view, a concept dubbed panpsychism. The debate gets thornier when you ask whose consciousness counts. Does a cat's observation collapse quantum states, a bacterium's? If the universe needs observers, why did it spend billions of years lifeless before minds evolved? Some theorists sidestep this by suggesting time is an illusion, that consciousness retroactively shapes the past, a twist echoing the delayed choice quantum eraser experiments. Others argue consciousness isn't creating reality, but selecting it from a multiverse of possibilities, like tuning a radio to one station out of infinite options. Is any of this science? Hardline materialists scoff, calling it metaphysics dressed in quantum jargon. Yet the equations don't lie. At its core, reality behaves differently when watched. Whether that's proof of a mind-dependent cosmos or just the limits of our measurement tools remains one of physics' most electrifying mysteries. The universe might not just be stranger than we imagine, it might be imagining us. What if the universe isn't just described by math? What if it is math? That's the radical proposition of Max Tegmark's mathematical universe hypothesis. a theory so audacious it strips reality down to its barest essence, pure abstract structure. No particles, no forces, no space-time, just equations. In this view, the cosmos isn't governed by mathematics. It's an embodiment of mathematical relationships, a giant self-contained formula where stars, planets, and even consciousness are just patterns in an infinite sea of numbers. Tegmark's argument begins with a simple observation. Mathematics has an uncanny ability to predict physical phenomena long before we observe them. Maxwell's equations predicted radio waves, Einstein's relativity foresaw black holes, and quantum mechanics described particles we wouldn't detect for decades. This isn't just convenience. Tegmark insists it's evidence that math isn't a human invention, but a discovered landscape. He takes it further. Every mathematically possible structure exists in some concrete sense. Our universe, with its specific laws, is just one thread in a vast tapestry of mathematical realities, some with different dimensions, forces, or even logic. But how do you test a theory where reality is literally made of math? Critics pounce on this. Science thrives on falsifiability, yet Tegmark's hypothesis risks being untouchable. If every possible mathematical structure is equally real, how do we verify or disprove it? Some accuse the idea of being more metaphysics than physics, a dazzling thought experiment with no empirical anchor. Even multiverse theories, often deemed speculative, at least propose observable imprints, like bubble collisions in cosmic microwave data. The mathematical universe offers no such fingerprints. Others push back. Maybe the test is simpler. If math is the fundamental layer, then the deepest laws of nature should eventually reduce to purely abstract relationships, free of physical baggage. String theory's equations, for example, already feel more like geometry than traditional physics. Or consider quantum mechanics, where particles exist in probability clouds until measured, a process eerily reminiscent of mathematical possibilities collapsing into definite outcomes. Could these be glimpses of math's primacy? The debate spills into philosophy. If the universe is math, what does that mean for us? Are our thoughts just algorithms humming in a cosmic processor? Tegmark sidesteps existential dread by distinguishing between baggage-laden math, human symbols like numbers or operators, and the intrinsic relationships they represent. The number 2 is a label, but the concept of duality exists whether we name it or not. In this light, consciousness itself might be a particular kind of mathematical pattern, a configuration of information processing that gives rise to subjective experience. Yet the theory's boldness is also its vulnerability. Without experiments, it risks joining string theory's controversial landscape, where elegance outweighs evidence. Some physicists propose indirect tests, like searching for fundamental symmetries or computational limits in nature signs the universe is running on a code. Others argue the hypothesis isn't science at all, but a kind of Pythagorean mysticism dressed in modern notation. What makes Tegmark's vision so compelling isn't its certainty, but its audacity. It forces us to ask, is math invented or discovered? Are we uncovering eternal truths or projecting our mental frameworks onto chaos? Whether the universe is made of equations or merely described by them, one thing is clear: mathematics remains the sharpest tool we have to carve meaning from the unknown. And that, in itself, is a mystery worth pondering. From the explosive birth of the Big Bang to the silent echoes of a holographic cosmos, from the infinite recursion of fractal universes to the unsettling possibility that we might be someone else's simulation, each of these theories doesn't just challenge our understanding of reality, it shatters it. They force us to confront the humbling truth that what we call common sense might just be a fleeting illusion, a temporary framework built from the tiny sliver of reality we've managed to observe. And that's the true magic here, not just the wild speculations themselves, but the way they expose how much we still don't know, how many mysteries remain lurking at the edges of our equations. Think about it, every generation of scientists has been certain they've nearly figured it all out, only for the universe to laugh and reveal another layer of complexity. The ancient Greeks believed in crystal spheres carrying the stars. Newton thought space was static and eternal. Even Einstein, for all his brilliance, resisted the idea of an expanding universe until the evidence became undeniable. Today, we stand at a similar crossroads, armed with better tools but facing even deeper questions. Are we alone in the cosmos, or is life a cosmic inevitability? Is time a river or a Möbius strip? Does the universe even care about our puny attempts to define it? That's where you come in. The most thrilling part of all this isn't the answers, it's the questions. The theories we've explored today aren't just academic exercises. They're invitations to wonder, to debate, to push the boundaries of what's possible. Maybe you're drawn to the elegance of Penrose's cyclic cosmology, or perhaps the sheer audacity of the simulation hypothesis makes your brain tingle. Or maybe you've got a wild idea of your own that no one's dared to put into words yet. That's how science moves forward, not by clinging to dogma, but by daring to imagine the unimaginable. So here's the challenge. Don't let the conversation end here. Dive into the comments and tell us which theory blew your mind the most, or hit pause and go fall down a research rabbit hole of your own. Share this with someone who loves a good cosmic mystery, because the universe isn't just stranger than we suppose, it's stranger than we can suppose. And that, more than anything, is what makes the journey so exhilarating. The search for answers isn't just about filling in gaps in a textbook. It's about embracing the wonder of not knowing and finding joy in the endless, beautiful mystery of it.